Welcome to Echoes and Atoms, where history meets science and ideas echo across time. Today, we embark on a journey beyond our solar system to explore the most mysterious visitors our cosmic neighborhood has ever received. Imagine objects traveling for millions, even billions, of years through the vast emptiness of interstellar space, carrying secrets from distant star systems and suddenly appearing in our solar system. These are interstellar objects, and they are rewriting everything we thought we knew about our place in the universe. In the next 30 minutes, we'll dive deep into the science behind these cosmic wanderers, explore the 3 confirmed interstellar visitors we've discovered, examine the technology that allowed us to detect them, and discuss what their presence means for our understanding of planetary formation, alien life, and the future of space exploration. From the cigar-shaped mystery of Oumuamua to the icy comet Borisov, to the newly discovered ancient traveler Atlas from ancient impacts that may have seeded life on Earth, to the revolutionary detection methods that are changing astronomy forever, this is the complete guide to interstellar objects. Let's start by defining what makes an object truly interstellar. An interstellar object is any natural body that originates from outside our solar system and passes through it. These cosmic travelers have hyperbolic trajectories, meaning they're moving too fast to be captured by our sun's gravity. To understand how remarkable this is, consider the scale. The nearest star to our sun, Proxima Centauri, is over 4 light-years away. That's about 25 trillion miles. For an object to travel that distance and enter our solar system, it must have been ejected from its home system with tremendous force, then drifted through the cosmic void for potentially millions of years. When planets form around young stars, gravitational interactions can fling rocky or icy bodies out of their birth systems at incredible speeds. These objects become cosmic nomads, wandering the galaxy until they encounter another star system like ours. Scientists estimate that at any given time, thousands of interstellar objects could be passing through our solar system. However, detecting them is extraordinarily difficult. They're typically small, dark, and moving at speeds of 20 to 30 kilometers per second relative to the sun. Most pass through undetected, visible only for a few weeks or months before disappearing back into interstellar space. Think about that. Right now, while you're watching this video, an ancient shard of rock or ice from a distant star could be silently gliding past Earth, and we may never even notice. The discovery of interstellar objects represents a new frontier in astronomy. Unlike studying distant exoplanets through indirect methods, these visitors allow us to examine material from other star systems directly. They're like cosmic messengers, carrying information about planetary formation, stellar evolution, and the chemical composition of distant worlds. October 19, 2017, marked a pivotal moment in astronomical history. Robert Warwick, using the Pan-STARRS telescope in Hawaii, spotted something unprecedented, a faint point of light moving across the sky at an unusual angle and speed. Initially catalogued as asteroid A2017U1, this object's trajectory quickly revealed something extraordinary. Unlike asteroids or comets that orbit our sun in elliptical paths, this visitor was following a hyperbolic trajectory, moving too fast to be gravitationally bound to our solar system. It was our first confirmed interstellar visitor, and scientists renamed it Oumuamua, Hawaiian for scout or messenger from afar arriving first. Oumuamua's physical characteristics were unlike anything astronomers had seen before. Measuring approximately 400 meters long and 40 meters wide, it had an extremely elongated shape, roughly 10 times longer than it was wide. This cigar-like or needle-like appearance was unprecedented among known asteroids or comets. Its surface appeared reddish, similar to objects in the outer solar system exposed to cosmic radiation for billions of years. However, Oumuamua showed no signs of typical comet activity, no tail or coma of gas and dust, despite passing close enough to the Sun where such activity would normally be expected. But perhaps most intriguing was Oumuamua's unexpected acceleration as it moved away from the Sun. This non-gravitational acceleration couldn't be explained by solar gravity alone. Several theories emerged. Outgassing of volatile materials too faint to detect, solar radiation pressure acting on its unusual shape, or more exotic explanations, hydrogen icebergs or even artificial origins. The artificial origin hypothesis remains speculative but fascinating. Harvard astronomer Avi Loeb suggested Oumuamua could be a light sail, a thin artificial structure propelled by stellar radiation. While this idea captured public imagination, most astronomers favor natural explanations. Yet here's the key. Oumuamua forced astronomers to admit we had never seen anything like it before. Its brief visit lasted only a few months. By the time astronomers realized its significance and organized detailed observations, it was already moving away from the Sun, becoming too faint for most telescopes. That sense of cosmic urgency, the idea that we only had a fleeting window to study this visitor, still drives the field today. In July of 2025, astronomers made history once again. The Atlas Survey telescope in Chile detected a faint but fast-moving visitor cutting across the night sky. Within days, it was confirmed. This was not an ordinary comet, but our third interstellar object. Designated 3I, also known as a TLS, it had come from far beyond the borders of our solar system. What made 3I so remarkable was its trajectory. The orbit was extremely hyperbolic, moving far too quickly to have been flung from our own solar system. Instead, it had been traveling through the galaxy for untold ages before arriving in our cosmic neighborhood. And this is no ordinary traveler. Estimates suggest 3I TLS is astonishingly old, possibly between 7 and 14 billion years of age. That means it could be older than the Sun itself, making it perhaps the oldest comet humanity has ever laid eyes on. In a very real sense, we are looking at a fossil from the dawn of the galaxy. Unlike the enigmatic Oumuamua, which baffled astronomers with its lack of cometary activity, 3I wasted no time revealing its nature. As it approached the Sun, it developed a glowing coma and a shimmering tail, classic signs of an icy comet heating up in sunlight. The Hubble Space Telescope even captured images of dust streaming away from its surface, shaped into a delicate arc by the pressure of sunlight. And it's not just beautiful, it's active. Observations show that 3I Atlas is shedding tens of kilograms of material every second. Imagine an entire car evaporating into space every few minutes. That's how much mass this comet is losing as it races through our system. Its path brings it closest to the Sun in late October of 2025, at a distance just inside the orbit of Mars. Don't worry, it poses no threat to Earth. Its nearest approach will be about 1.8 astronomical units away, roughly 270 million kilometers. Safe by cosmic standards. Yet, its orbit has raised eyebrows. The alignment of its path lies close to the plane of the planets, the ecliptic, which is unusual for an object from interstellar space. This has sparked speculation. While most scientists are confident 3I is a natural comet, some have suggested more exotic possibilities. Could it be a fragment of a shattered world? Or, as a few daring voices have proposed, could it be something artificial, perhaps even a probe, built by another civilization? The idea is speculative, but it adds a sense of mystery to this ancient visitor. What makes 3I especially exciting is the possibility of a mission. Some researchers have pointed out that NASA's Juno spacecraft, currently orbiting Jupiter, could be redirected to intercept Atlas in 2026. If successful, It would be humanity's first chance to meet an interstellar object up close, an encounter that could change everything we know about how planetary systems form across the galaxy. So, in 3i Atlas, we find both a relic of unimaginable age and a new opportunity. It is a messenger from deep time, carrying within it the chemistry of a star system that may no longer exist. And as it passes through our skies, it reminds us, interstellar objects are not rare flukes. They are part of the galaxy's natural rhythm, drifting endlessly between stars, waiting for us to notice. Just 2 years after Oumuamua's historic visit, amateur astronomer Gennady Borisov made another groundbreaking discovery from his observatory in Crimea. On August 30th, 2019, he spotted what would become known as Comet Borisov, our second confirmed interstellar visitor. Unlike its mysterious predecessor, Borisov behaved exactly as astronomers expected an interstellar comet should. As it approached the Sun, it developed a classic comet tail, streaming gas and dust behind it as solar radiation heated its icy surface. Borisov's composition revealed fascinating insights into planetary formation in other star systems. Spectroscopic analysis showed it contained water vapor, carbon monoxide, and other compounds similar to comets in our solar system, but with some intriguing differences. The ratio of carbon monoxide to water was higher than typical solar system comets, suggesting it formed in a colder environment around a different type of star. Its nucleus was estimated to be 1 to 16 kilometers in diameter, significantly larger than Oumuamua. Its orbit indicated it had been traveling through interstellar space for potentially millions of years, before entering our solar system at a speed of about 32 kilometers per second. Remarkably, Borisov maintained its structural integrity during this long interstellar journey. Computer models suggest it likely originated from a red dwarf star system, where lower stellar temperatures would allow icy bodies to form farther from the star and be ejected more easily through gravitational interactions. The study of Borisov provided the first direct comparison between material from another star system and our own solar system's comets. It showed us that while the basic building blocks of planetary systems appear similar across the galaxy, subtle differences in composition reflect the unique conditions of their formation. In a way, Borisov was the perfect control experiment to compare against Oumuamua's mystery. One looked familiar yet subtly different, the other alien and puzzling. Together, they told astronomers that the universe of interstellar visitors is going to be diverse and unpredictable. The rise of interstellar object astronomy is inseparable from the revolution in astronomical survey technology. For centuries, astronomers relied on manual observations, but the sheer scale and fleeting nature of interstellar visitors made them virtually impossible to detect until now. The breakthrough came with the advent of automated wide-field sky surveys that can scan immense swaths of the heavens night after night, capturing the subtle movements of objects as small as a few dozen meters across. At the heart of this revolution is the Pan-STARRS telescope system in Hawaii. Pan-STARRS, short for Panoramic Survey Telescope and Rapid Response System, uses a powerful combination of wide-field optics and advanced image processing algorithms. It can image the entire visible sky several times each month, comparing millions of data points to identify new or moving objects. But Pan-STARRS is just one player. Other major surveys, including the Catalina Sky Survey and NEOEYES, use similar techniques. Machine learning algorithms now sift through the data, distinguishing between known solar system bodies, background stars, and potential new interstellar discoveries. Astrometry measuring the precise positions of objects over consecutive nights is crucial. If an object is moving too fast to be bound by the sun's gravity, it's flagged as a candidate for interstellar origin. This process requires rapid coordination, as these objects can fade from view within weeks. Looking ahead, the Vera C. Rubin Observatory in Chile is set to transform our capabilities even further. Its Legacy Survey of Space and Time, LSST, will image the entire southern sky every few nights with unprecedented sensitivity. Scientists anticipate that once operational, it could detect dozens of interstellar objects each year, offering a steady stream of new discoveries. In other words, what was once a once-in-a-century event could soon become a routine part of astronomy. To understand where interstellar objects come from, we have to look at the chaotic early years of star and planet formation. Around every young star, swirling disks of dust and gas protoplanetary disks serve as the birthplaces of planets, asteroids, and comets. But this process is anything but orderly. As planets coalesce, their gravitational fields interact, often violently. Smaller bodies are hurled in all directions. Some fall into their star, others crash into larger planets, and a significant number are ejected entirely, flung into the vastness of interstellar space. Simulations show that for every planet successfully formed, thousands of smaller bodies are likely cast out. Giant planets like Jupiter act as gravitational slingshots, efficiently ejecting material from their home systems. This process, called gravitational scattering, is universal, meaning every planetary system in the galaxy is likely contributing to the population of interstellar objects. The composition of these objects offers clues to their origins. Oumuamua's reddish hue and lack of observable ices suggest it formed close to its star, where heat stripped away volatiles. Borisov, in contrast, is rich in ices and carbon monoxide, indicating a birthplace in the cold outer regions of a system, perhaps around a red dwarf star. Atlas, older still, may carry signatures of environments that existed when the Milky Way itself was young. What's even more fascinating is the diversity these objects represent. Some may be fragments of shattered worlds, others pristine relics from the galaxy's earliest days. Their ages can span billions of years, predating our own sun, or be relatively young, ejected from recently formed systems. And here's the twist. Our own solar system is also a contributor. Over billions of years, Jupiter and other giants have ejected millions of asteroids and comets, sending them on interstellar journeys. Somewhere out there, another civilization might one day discover a visitor from Earth's backyard, a cosmic ambassador carrying clues about our own origins. The arrival of interstellar objects is a scientific goldmine. For the first time, we have the opportunity to study material from beyond our solar system directly, rather than relying on remote observations or meteorites of ambiguous origin. Every new object is essentially a sample return mission delivered to us by the galaxy itself. One tantalizing implication is panspermia, the idea that life, or at least its building blocks, could hitch a ride on interstellar objects. If microbes can survive the harsh conditions of space, comets and asteroids could serve as cosmic delivery vehicles, spreading life throughout the galaxy. While there's no direct evidence yet, the possibility adds a new dimension to our search for life beyond Earth. The study of interstellar objects also informs our understanding of planetary system diversity. By analyzing their composition, structure, and dynamics, astronomers can infer the conditions present in their birth systems. This helps answer fundamental questions. Are planetary systems like ours common? What kinds of planets form around different types of stars? How unique is Earth in the galactic context? Technological advances are driving this field forward. Rapid response observation networks now mobilize telescopes worldwide within hours of a new discovery, maximizing the scientific return before the object fades from view. The European Space Agency's Comet Interceptor mission, launching soon, is designed to wait in space for a suitable target, ideally an interstellar object, before racing to intercept and study it up close. Future missions may go even further, using advanced propulsion like solar sails or ion drives to chase down these fast-moving visitors. Some proposals envision interstellar object interceptors parked in orbit, ready to launch at a moment's notice. The dream is to capture, sample, or even return material from an interstellar object, unlocking secrets about the chemistry and physics of distant worlds. Statistical studies are also revealing the true scale of the interstellar population. It's estimated that at any moment, thousands of interstellar objects larger than 100 meters are passing through our solar system. Most go unnoticed, but as detection technology improves, we'll begin to see just how interconnected the galaxy truly is. We stand at the threshold of a new era. What began as rare, serendipitous discoveries will soon become routine. As the Vera Rubin Observatory and next-generation space telescopes come online, the catalog of interstellar visitors will grow rapidly. Each new object will bring fresh insights, challenge our theories, and perhaps even upend our understanding of planetary formation and the potential for life elsewhere. The study of interstellar objects is more than just an astronomical curiosity. It's a bridge between worlds. These visitors remind us that our solar system is not isolated, but part of a vast, dynamic galaxy where matter, and perhaps life, is constantly exchanged. They are time capsules, messengers, and cosmic storytellers, offering us glimpses of places we may never visit. As we look to the future, the possibilities are endless. Will we find evidence of life? Will we discover materials or structures that hint at advanced civilizations? Or will we simply marvel at the stars,